61A, Lecture 29, Q&A.
Hey, John, while we wait for somebody, it's been a while since I've written a compiler and interpreter, but I remember we used to use these, it was Lex and Yak and Flex and Bison, these sort of where you can specify the grammar and then it would build it for you. Is that still sort of popular in use?
Yeah, so we're doing a very unusual thing in today's lecture, which is to describe how you would write a parser kind of from scratch.
Yeah.
And right, so these other tools aren't kind of procedural. Instead, you just describe the grammar and then there's a generator that builds the parser for you. Now, if you actually looked at that parser, it would look kind of like the code that we looked at today. So so that's kind of how a parser works. But do people actually sit there and write parsers? No, especially for something as complicated as Python. You just wouldn't do it because there's too much like chance for error.
Right, right. So I think there's another level of abstraction. There's like, it's sort of cool. Like there's this code where you can have this higher level description of your language that then writes the parser that then compiles or interprets the code.
Yeah, I mean, basically, the field of programming languages attract a lot of really good programmers. You can imagine why. So there's really nice tools for that.
Yeah. Hey, can you tell me so the last tools that I use were Flex and Bison. Is that still the popular ones, or things have moved on since then?
I don't know. It's a good question. I think they're still around, but there might be new ones. I don't think that the ideas have changed too much.
Yeah, I think that's my understanding too, but it's been a little while.
Okay, so the question was, in scheme read, there's a pop, and shouldn't that pop remove something from the end rather than the beginning? Well, maybe pop was a bad name for it, but what this source object is not actually a Python list, but instead it's this, where is it? It's this thing called a buffer. Oh, I guess it's in a different file. And this buffer has a notion of pop that doesn't remove things from the end, it removes them from the beginning. So maybe we should have called it something else. But that's the answer to the question, why is it the case that popping is removing stuff from the beginning of the line? It's because what you're removing from is not a list, but a buffer, which basically tells you about the future. And when you pop something from it, you get the first thing.
And Sandra, the term pop and push is generally referred to stacks and queues. And pop, I always think of pop is what's at the very top of something, but I think it is overloaded depending on what the underlying data structure is.
Right, we could definitely blame Python here, which has a kind of unconventional notion of popping being from the end, but that's okay.
It's just a question of where you define the front, the end doesn't have to be the end. Well, anyway, it doesn't matter. But yes, it's from the front in this particular case.
So we didn't really go over this in lecture, but it is definitely worth looking at this class buffer. The implementation doesn't matter much, but its behavior does. Basically, you get this iterator over a bunch of symbols like open parentheses and pluses and numbers and close parentheses and stuff like that. And then the goal here is to give you the next thing and remove it, or just peek at the next thing, but not remove it yet. And there's a way to print it out, which is used in some error messages. Yeah, great question. So the question is, in scheme read, you hit or for parsing in general, you hit a base case when you've reached a symbol or a number, something that's not a combination, not a composition of stuff, but just like one thing. What happens when you reach that base case? How does it kind of work its way to the next open parenthesis? So let's look at an example. I'll try to answer the question. If you have something like plus 1 minus 2, 3, whatever. You're trying to figure out what this thing is. Right now, it's just a bunch of symbols. I'm going to separate them by spaces so that you can see them all. So now we have 1, 2, 3, 4, 5, 6, 7, 8, 9 things to worry about. The original call will be to effectively the whole thing. And it begins with an open parenthesis. So we make a recursive call on the rest. So with an original call to scheme read, we've begun another call, which, by the way, if you look at the structure of this thing, it doesn't actually call scheme read, it calls read tail, which basically just calls scheme read a bunch of times until it finds the matching closing parenthesis. So that's going to be this story, is that once you see an open parenthesis, you keep reading the next thing until you find a matching closing parenthesis. If when you read the next thing, it's a base case, well, that was in another recursive call. You reached a base case, you return like, oh, this is just a plus symbol. But where do you return to? You return to the process where you were going to read all this stuff until you found the next closing parenthesis. So that's kind of the story, is like when you hit the base case, you return, but where you're returning to is an ongoing reading of some long expression that you know started with an open parenthesis because you read it at the beginning, and you're just kind of going to keep reading stuff until you find a closing parenthesis.
How do we peek at the next item in an iterator without removing it?
Oh, great question. The answer is you can't,
No.
which is why we have this buffer class that we provided. So we can just take a look at it really quickly. It kind of turns stuff into lists as you go. So you get a bunch of iterators coming in, but what it does is it just stores everything that it's seen in this thing called lines. And when it needs to see something new, it will go ahead and get more stuff from the source iterators, but not necessarily advance. So you kind of like keep track of the whole list of things that you've seen and where you are. And that's the story, is like if you have a data structure that allows you to peek at something without popping it off, then you can do it, but a standard iterator wouldn't be able to do it for you. You could read this whole implementation if you want. It's like a little bit long. And the reason it's a little bit long is so that it can print out the whole code and where you were in the code, which is helpful for error messages.
John, how is this different than a stack or a queue?
Well, in this case, we're never really adding stuff. Like we're removing stuff from the beginning and we're adding stuff to the end. So it's a lot like a queue.
Yeah.
Except for like it's a queue that remembers what you've removed just in case you need to print it out.
Okay, so, and I don't think that the built-in Python queue, I think it's the deck class, allows you to do that. Yeah, there's no memory.
That's right.
Okay, all right. So it's that little memory that it wants you to have. That's the...
And the only reason you'd have that is just so you can like print out, you know,
yeah,
we were here.
Yeah, gotcha. Okay.
Yeah, good question. So here we are, we're in calc eval. If it's a pair, meaning we're now evaluating something that begins with an open parenthesis, then what does this line mean? exp.second.map calc eval. Well, to figure that out, we got to know what an exp is. It turns out it's a pair, which we figured out here. So let's go take a quick look at what a pair is and what its map method does. Scheme reader. Here's the pair. It's got a first and a second. It's a linked list or like a scheme linked list. So the first can be anything, but the second should be another instance of pair or nil to represent the end. I guess we didn't talk too much about this kind of thing, but this just lets you get like the length of a list or use square brackets. Did we talk about this at all?
I don't think
I think maybe we left that out this semester, but it's not that important. But what is important is there's a regular old method called map. And what it does is it takes in a function. It calls that function on every element of the list that this pair represents, and then returns a new list, which is really a pair instance. So it's a linked list kind of structure with all the results of calling this function. So, and we can read this pretty straightforward. Like you call fun on the first element. If there's a second element, then you recursively call map on the second element. And you build a new list that's got this new first element in it. This doesn't say exp.map calceval, instead it says exp.second.map.calceval. I think it's worth looking at an example. So this example here, which looks a little bit funny, is really add 2 to the result of multiplying 4 and 6. This thing, if we put it into...
You dropped that paren, John.
Reader, oh my goodness. If we put this into the reader, we can see what it looks like from Python's point of view. It's a pair that starts with a plus, and then a 2, etc. If I get the dot second of this object, it's all this thing, which really only has 2 elements. It's got the number 2, and it's got this sub-expression times 4, 6. So the point of mapping calceval over this is that we are converting the 2 to a 2, and we're converting the times 4, 6 into its value. And then it's time to add. That's what calc_apply does. So the point of this is it's the recursive call that takes all the sub-expressions and finds their values. I probably could have just said that one sentence and it would have been more clear.
Always more clear. It's always the last sentence, but you still have to get there, John. It's important.
Yeah, good question. So the question is, should you regularly use map to make recursive calls if your input is a list? And I think that's not always the case. It really depends on what you're trying to achieve. So you've written some function. Let's say S is an instance of a pair, like it's a scheme list. Whether you use map or not really depends on whether you're making recursive calls on the elements of S, in which case map is appropriate, or if you're making your recursive call on the rest of S, in which case map won't do that for you. You just have to explicitly call F on S.second. So yeah, I think that eval is unusual in that it's not linked list processing where you're just like doing something the first element and you're doing a recursive call to the rest of the list. Instead, what it's doing is making its recursive call on each element of the list, and that's why we use map.
The next question was, what is the main decorator?
Yeah, so this main decorator is something that's specific to 61A. And it just says, if you run the file, this is the function that should be called. So if I run the whole scalc.py file, it's not going to call as scheme list. Instead, it's going to call read eval print loop and do whatever's here.
The other way that this would have worked is just leave off the definition of read eval print and just have that while loop be the body of the code, and then it would run it. This is a cleaner way to do it, having everything in a function.
Yeah, exactly. So we'd get the same result if we just did that. The only issue with this is that if you import this file from another file, then this would run, which you don't always want. There's kind of an ugly convention in Python, which is that most times when you see like commercial Python code, you'll see them write that, which I felt like we'd spend so much time trying to explain what this was that it would ruin the course. So that's why we introduced the main decorator.
I think that's a bit of an exaggeration, John. But I also find that syntax hideous. So I'm glad you put in a nice clean version of it.
And by the way, it's just defined in this ucb.py file, which was written long ago when I started teaching this course. And it's got this kind of same weird notion of name equals main kind of buried in there. So that's all it does.
The next question was, wouldn't a parser for Python need to track indentation instead of just ignoring whitespace?
Yeah, that's right. Indentation is part of the grammar of Python, meaning that the parser needs to not just ignore all of the spacing and indentation like we're doing for scheme, but it has to track it.
I mean, that's why most languages have a notion of a begin and an end, right? So I guess Python has the notion of a begin, that's the colon, but the end is implicit in the indentation. I've averaged never liked that. I prefer to have like an explicit open close begin and curly bracket, curly bracket. So I think it makes the code a little bit easier to read. But yes, in this regard, you have to keep track of it. Otherwise, you don't know when the body of anything ends.
Yeah, I see. Thank you. Yeah, same. I think like it's better to have something to keep track of beginning and end, just to make it clear.
John, do you know if there was a reason for that? I mean, it's a little bit of an unusual convention in Python.
I agree it's unusual. I think there was some story I read once about how they decided this. And
yeah, okay.
I believe it involved having someone's spouse read a piece of code when they weren't programmers or something like that. And they're like, oh yeah, this makes sense to me or whatever. But I don't know how true that really is. But
yeah, well, let's make it true. I like stories like that.
Well, if you like explicit punctuation telling you where things end, then I'm sure you'll love Scheme because it's got lots of closing parentheses.
Oh man, but that's a whole nother world of hurt.
The next question was, what programming languages are typically used to write an interpreter?
It's a great question. I think that it depends on what your goal is. If you're building an interpreter that thousands of people are going to use and they're going to run big programs on it, then the primary concern is usually speed and resource use. At the time that Python's interpreter was written, C was the obvious choice for writing a program that would run fast. What's kind of fascinating is that now the fastest implementation of Python is not the one that we all use, but instead a separate one called PyPy, which is a Python interpreter written in Python. And it's quite a bit faster than the Python interpreter written in C. It has achieved this speed through some very clever engineering, where basically like the Python code is not interpreted. The Python code that runs the interpreter is not interpreted, but instead kind of compiled and optimized in various ways. Like I said, programming language folks tend to be pretty clever at programming. So there's basically that story of, what's the right programming language in order to make this interpreter fast? An interesting trend in the programming language community is that for any general purpose programming language, oftentimes people will try to write an interpreter for that language as one of the first large programs written in that language.
Yeah.
Why? Well, it's kind of like a natural target, and the people writing the interpreter, they don't know, they don't write many other things except for interpreters. So that's how it goes. So that means that interpreters have been written in many different programming languages, and different programming languages can be surprisingly well suited for this. I'm not sure there's like an obvious best one, except that if I were to commit to one, it would probably be something that's kind of an evolved version of Scheme called Racket. And there's this wonderful community of programmers and developers that still contribute to this language called Racket. And they've set it up so that people can create variants of the language like really easily. And there's all kinds of tools to make sure that like your new variant actually works correctly and stuff like that. And I think that's led to a fair amount of productivity. They've got versions of the language that are good for teaching. They've got good versions of the language that are good for, like building websites and stuff like that. So occasionally there have been some like standouts, and I think C was one because it was just fast. And I think Racket is a modern one because it happens to work well.
Yeah, I'm surprised to hear that the Python interpreter is faster than the C, although I imagine with the same clever engineering, you can make the C faster, because it's hard, if somebody's asking the question, is C still faster than Python even with the PyPy upgrade? I can't imagine that Python is going to be faster than C.
No, though there's an interesting project called Cython, which is a subset of Python. So you can't do everything you can do in Python, but you can do most of it. So the code more or less looks like Python code, but it can be compiled. I think the way they compile it is that they translate it into C.
Yeah.
And then they run a C compiler. I believe that is why it's called Python.
Yeah.
But that means that a lot of times when people are trying to write fast code within like a Python ecosystem where they've written most of their code in Python already, they just switch to this language, which is not actually C. It looks more like Python, but it can be translated into C. And that's how they kind of run their part that needs to write their part that needs to run really fast.
I see. I see.
A follow-up question was, if you're going to write a Python interpreter in Python, don't you also need a Python interpreter written in something else?
Yeah, that's right. So in order to get this Python interpreter written in Python to work, they had to run the interpreter using the C version of the interpreter that already existed. And once they've done that, then they can run their own interpreter. So you get these very strange cycles. But your intuition is exactly right, that you kind of have to have something that already runs in order to build something new.
Right. Yeah. And John's right. The folks who do programming languages for a living are incredibly clever.
Yeah, it sounds like it. Thank you.
Yeah. By the way, if you get a chance, take a PL course. I'm sure there's one offered here. Yeah, John?
Yeah, it's numbered 164 and it's a good course.
Yeah. I mean, I don't know if it's the most practical course, but I think thinking about the nature of different languages and is really, really cool, and understanding how these things really work is super interesting just from a sort of purely intellectual perspective.
Yeah.
Thanks. Okay. Thanks, Malika. Mashan is up next. Sorry about that, Mashan.
That's all good. So we talked about like the languages that you could use, but is the structure for writing interpreters like the same? Like, is it still this recursive structure, or are there other ways to do it as well?
Yeah, good question. This recursive structure that I've shown you is the simplest and probably the slowest way to interpret code. Most of the stuff that actually happens in your computer these days doesn't just do this, but instead makes transformations to the original program along the way. And this is actually how Python's interpreter works, is that it takes a piece of code that might run many times and generates some like efficient version of that and then runs that many times, which is like a step that we haven't talked about in this course because it doesn't change the answer, it just makes it run faster. If you want to go really deep into this, there's the original textbook for this course called The Structure and Interpretation for Computer Programs, has a 5th chapter that was never covered in 61A, even when even when the whole course was Scheme. So the 4th chapter is about interpreters, and that's basically what we're covering now. But the 5th chapter was about how you get a programming language to actually run on a chip using a limited instruction set that doesn't have things like procedure calls and stuff like that. And they did a very nice job of laying out how you would get from a high-level language to a low-level language. And so, people who are excited about this idea of building programming languages should all go read that chapter. You can read the whole book too. You'll find many things familiar from what you've learned in 61A.
When did you switch over, or when did we switch over from teaching Scheme in 61A to Python?
We switched in 2011.
Wow, that's late.
And yeah, that was the first time I taught the course.
Yeah.
I didn't just teach it, but I kind of redid it. And that was a lot of work.
Yeah. That came pretty late because most of us had switched over. Well, a lot of people switched over to Java for a while before Python came on the scene. But then once Python came on the scene, it was clear that was the right place to start.
Yeah, Berkeley was definitely a holdout.
Yeah.
There were some.
I think there's still a few
folks who are a big fan of Scheme, and
I think
that's reasonable.
It's something.
But I kind of like the idea that the community around Python is so big that if you want to build some like random thing in your free time, you can kind of Google about it, and there's always some guide. That we did see a big uptick in kind of student independent projects and hackathons and stuff like that right at the same time. So you never know about cause and effect, but it does seem like they're probably related.
Joy asked a good question. Which factors do you consider when picking languages for a coding project? Well, I'll tell you what I do. Although I work probably at a different scale than John does, is so part of it depends. Am I just trying to hack something together to try something out? And if I'm doing that, it's almost always MATLAB or Python because those are just the ones I'm comfortable with, and I can code really, really fast in. And they've got a lot of built-in libraries, so I don't have to re-implement everything from scratch. So if I'm just putzing around on a research project, it's always Python or MATLAB. And then if I think I'm probably going to deploy something on server or web-based, probably, you want to stay away from things like MATLAB because those are proprietary and you can't really run those in the software. So then you start thinking JavaScript, maybe Python and Java, some combination of Python and JavaScript. Then every once in a while, we're doing things where we really, really need speed. We're doing things that are computationally super intensive. And then you just bite the bullet and you implement it in C. Usually what I do is I implement it in Python, make sure it's working, debug everything, get it all working, and then translate it into C. Because writing C code from scratch can be a little excruciating because you have to do all the memory management. And I find it a little bit harder to debug the code. So I guess it's a combination of, and one more thing too, is the scale at which you're going to be writing. So if you're writing something really, really big, you stay out of programs like MATLAB because they weren't built. Python is reasonably good for large scale. And then the last part of that is every once in a while we do something where we really have to be cross-platform. So I know that this is going to have to run on Linux, Mac, and Windows, and then you do Java. I hate it. I don't like Java. It's painful. But if you really, really want cross-platform, I go to Java.
Yeah, I guess one way to summarize it is you actually want to solve as few problems as possible. Right? So you look for languages that have already solved many of the things that you'll encounter, if that's cross-platform or if that's kind of deployment or whatever.
Yeah. That was a really nice condensed version of my answer. What do you mostly code in, John?
We wrote a lot of Python these days. Yeah, because there's the support for kind of machine learning, deep neural network stuff is just better there than anywhere else. Okay.
Delania asked an interesting question. What are your priorities when learning a new language? Here's the thing you're going to discover pretty soon is learning a new language is, for the most part, pretty easy. Because once you know the basics, all the languages, I mean, there's a few exceptions like ML and Prolog and Haskell that are a little quirky. But once you know a handful of languages, it's like a couple of days. And then it's really, you can write in that language quickly. It's a question of how good is the code and how easy it is. But a combination of Stack Overflow and just your base knowledge. So I think Python is probably the last new language I've learned in recent memory. I don't know that I think the combination of JavaScript, MATLAB, Python, C, and Java, I don't know that, I guess R, I learned recently R, the statistical programming language, which took like all of an afternoon, frankly. I mean, it gets pretty easy after a while.
Yeah, I mean, reading a book often will leave you with very fleeting knowledge. You just got to go build something.
Yeah, you just got to start coding. Yeah, that's exactly right. Yeah.
So if I really just want to learn the language for the language's sake, then I usually just re-implement the Hog project because that's always that always makes me happy. But usually when I'm trying to learn some language, it's because I'm trying to do some particular thing in advance that actually matters, and I just like learn what I need to know in order to do that.
Yeah. It's source equals buffer input.
Yeah, so the question is, what is this line, which calls this function, which makes a buffer out of the result of tokenizing the lines of an input reader. The reason there's 3 parts to this is that they all do slightly different things that you need to compose together. This gets you the text. This breaks the text into tokens, which we talked about, like individual numbers and parentheses and stuff like that. And buffer gives you a way to walk through them one by one and remembers where you were just in case you need to print out an error message. So those are the 3 parts. And the part about reading is, I wish it were simpler, but I think it's unfortunately not.
Yeah.
If you look at the input reader, it is simple.
Oh yeah, just the input command.
Oh, good, because it's all built into Python. Yeah, so
Yeah,
Python has this notion of input, where if I call input, then if I type something, then that's the return value.